session. And the first talk is by Deeksha Adil. So yeah, thank you.
Thank you for coming this early in the morning. And I'm going to speak about some fast algorithms for regression problems. So this is all based on joint work with some of my collaborators. Some of them are here in the audience. So it's Brian, Rasmus, Richard, and Sushant. And these are based on a bunch of works over the last couple of years. And I hope to give a summary or like an easy summary of all of these. Okay, so just to set the notation, let's start with like the basics. So what do we aim to do in regression? So let's say you have some m data points and they all have n parameters. So let's think of it as you have more data points, few parameters. And the goal is you want to figure out, okay, which curve fits this data the best, like which goes through it the best, minimizing some distances. So in most of these, so let's just call these points, A, I, J. So like think of A as these row vectors and you have these labels on each of these data points. And now in most of the common studied things where is linear regression, you assume that, okay, there's a linear curve that fits this data and you want to figure out what that linear curve is. To be a little more formal, you assume there's some linear relation and you want to minimize this error vector. And the standard formulation asks you to just minimize the Euclidean norm of this error vector. And this we know how to do exactly. There's a nice closed form solution for this. But in some applications, you might actually want to think of, instead of minimizing the Euclidean norm, you think of some other function of the error that you want to minimize. And let's look at some. So one example is just that, okay, instead of looking at the Euclidean norm, let's minimize the LP norm of the error. And an example where this actually might be useful is, so let's think of a graph. And the goal is to send one unit of flow, say from x1 to x5. And you want to minimize some sort of energy. So you're given this graph, you want to find values that minimize, some energy, which is usually can be thought of as the electrical energy for those familiar with graph algorithms. And this can actually be cast as a regression problem. And you can think of it as, can exactly formulate this in like, okay, minimize some quadratic term under some constraints with very few constraints. And this matrix is just the edge vertex incidence matrix. And you can also, translate this to the formulation we were looking at. But now this is more like, oh, you have very few labels. You have very few, this B vector is really small. And you have like a lot of data points. Right. So this is more like the setting where you have very few labels. Now, if you want to fit something in these kind of models, there's this paper that runs some experiments along with studying some algorithms. So they look at different values of P while trying to minimize the P norm of the error vector. And so this is more like in two-dimensional space, they take some 10 to the 5 points, and only 2 of them have labels. And when you plot the labels, like in 2D space, you can see that when P is 2, it's like along the label points, you have 2 spikes. So this is not a good fit in that sense. But as you keep increasing P, it becomes more and more like a linear surface. So in some settings, in these settings, like more in terms of, this exact problem was more in the context of graphs, semi-supervised learning in graphs. So in these cases, it has at least been shown that for different P, for larger values of P, you can actually fit it much better. So there are some other things people can use, which is something like logistic regression, which is mostly used in the case of classification. And then this is like softmax regression, which is used in terms of finding smooth approximations to the max norm. But let's focus today on P norm regression for, let's say, P larger than 2. Right. So our formulation so we'll focus on this formulation where A is this tall and thin matrix. So you have more constraints, less variables. And B is the labels on these, or like on these data points. And yeah, right. So yeah, the goal is to just find a vector X that minimizes this. Okay. So okay, so an equivalent and easier formulation which we will use is, the instead of the over constraint setting, we'll just look at the under constraint setting. And I claim that they're both equivalent. You can translate from one to the other. And for ease of notation, we'll use this, but all the algorithms I present directly work for the over constraint setting as well. So in this case, we're just looking at, okay, this is more like you have a hyperplane, and you want to find a point on the hyperplane that minimizes the LP norm of, that has the minimum LP norm. So now A is a short fat matrix, and let's say it has dimensions n by m. And the variable has m coordinates. So look at this setting for now. Okay. Yeah. Okay, so some more advantages of LP norms. So it easily captures the Euclidean norm, yeah, the standard linear regression, which we know how to solve exactly. When P is 1, it's equivalent to linear programming. And when P is infinity, it captures like max flow, like linear programming, and a bunch of these things. So as P tends closer to 1, when P is less than 2, closer to 1, you tend to get more and more sparse solutions. And as P is large, as we saw in the example, you kind of get more flat solutions for applications. Okay, good. So before I get into algorithms, are there any questions?
So P is at least one that you're talking about.
Yeah, P is. But most of the algorithms I'm going to present will just look at P greater than 2. So we can do it fast. Okay, so to formally state the goal, so given some epsilon, what we want is we want to find some x that satisfies the constraint. So you want ax equals b, and you also want that the norm of x is at most a multiplicative factor away from the optimum. And we also want to be able to do this in some runtime that's polynomial in m, which is the size of the variable. And we want to be able to converge geometrically. So you want a log 1 by epsilon convergence rate. The advantage is in this case, you can basically solve to a polynomially high accuracy with only like polylog overhead. So this would allow us to, these are usually termed as high accuracy solutions. And because of this, you can actually converge really close to not just the objective, but also the solution value in most cases. Okay. And we would use the fact that we know how to solve this problem for p equals 2, which is just solving one linear system. Okay. So some of the previous works, they were all based on some convex programming, ellipsoid methods. They can all obtain high accuracy solutions, but they required some polynomial in m time, which was not a small polynomial. The work of Nesterov and Nemirovsky in 1994 was based on interior point methods, and these problems they were able to reduce solving the LP regression problem to just from square root m linear system solves. So it has root m iterations. Each iteration is solving an L2 problem or like a linear system. So this was till 1994. We knew this. Further, in 2018, stock 2018, Bibek, Cohen, Lee, and Lee, they give a new homotopy method. So this can do better than IPMs, especially for small values of P. So asymptotically, instead of m to the 1/2, you now have m to the 1/2 minus 1 by p. And asymptotically, this is the same as IPM for p closer to 1 and close to infinity. But for other values of p close to, let's say, 4, 5, or like some good values, this is significantly better. So you can see this here. And you can see that this is this problem is kind of symmetric around 2. And yeah. So basically, this is the dual of p norms is just some p by p minus 1 norms, and these are symmetric around 2, so you see this good symmetry around 2. Okay. So the first thing I'm going to talk about is a faster algorithm that we gave a few years ago, and this is able to obtain a high accuracy solution, but it's faster than the known method. So asymptotically, instead of going to m to the 1/2, we now converge in m to the 1/3 iterations to the optimum, and we still get a high accuracy solution. And this is not just asymptotically. For all values of p, you can actually do better. There's also this work by Bullens in 2019, which obtains this faster rate for p equals 4, and that's based on a completely different set of techniques, more optimization based, and these are, yeah, I'll get into how we get these rates. And we also believe this rate is optimum, though it's still open to proof. So given that you can only solve linear systems, we believe this rate is optimum. And it's also, in some contexts, they have proven a lower bound, which I will get to a little later in the talk, but not in this exact model. Okay, so you may ask, does this imply faster linear programming? Because p equals 1 and infinity correspond to linear programming. And the answer is no, because we have these factors of p linear, some p squared or p factors in the runtime. We can actually improve this to a factor p. So p must be away from 1 and infinity, and it's still a big open problem if you can do m to the 1/3 iteration algorithm for 1 and infinity. High accuracy, in the high accuracy regime. And okay, so now let's look at the algorithm. So the first algorithm, it's basically has two key components. The first part, which is iterative refinement, this helps us get the high accuracy part. The second part is a fast multiplicative weight update solver, and that allows us to improve from m to the 1/2 to m to the 1/3 iterations. So let's start with what we mean by iterative refinement. Before I do this, are there any questions? Okay, so iterative refinement, I mean, originally studied for linear, for just the L2 norm problem. It just means that if you're at some point x and this is your problem, you take a step, you go from x to x plus delta, you can reduce this to just solving this problem, which is just a quadratic problem, and we'll term this as the residual problem. And if you can solve this residual problem to some approximation, let's say a kappa approximation, you can solve the original problem to any accuracy you want with just kappa log m by epsilon iterations. So this idea was for simple L2 regression problems, this follows through. You just have to solve another quadratic problem. Why is this easier is a different question, and we'll see why does this help for LP regression. And this idea has also been used for smooth and strongly convex functions, especially in optimization. So where you, instead of writing this exactly as a quadratic, you can give nice quadratic global upper bounds, which comes from smoothness. And you can also give nice quadratic lower bounds, which follows from strong convexity. And once you have the same kind of upper and lower bounds, you can basically, can show that you can find minimizers to the upper quadratic problems, and all you need is some L by something like a condition number and some log 1 by iteration to convert to high accuracy solutions. And you can also do this approximately. You don't really need to minimize the upper bound exactly. So any approximate solution would just entail an additional kappa factor. Yeah, rate of convergence. Okay. So the problem with LP norms is, since we know how to solve quadratic problems, we would ideally want upper and lower bounds that are quadratic. But for LP norms, we can't say anything. It's too steep beyond a certain point and it's too flat around the origin. So you can't have any kind of quadratic approximations. So the hope is, okay, can you give any global upper bound and the same kind of global lower bound? Because if you have that, we could use some of the ideas of these iterative refinement and hope to do the same kind of thing. And the answer is yes, we can actually, yeah, this would allow us to essentially convert a constant approximation to a high accuracy solution. And the answer is yes, we can actually give good envelopes. So we can write upper, so we basically can, yeah, the answer is we could actually find some good envelopes and then you can just minimize the upper bound approximately and we converge it. Hopefully this will. Okay, so how do we construct these good envelopes? So let's look at the simple case of p equals 4 and let's look at one coordinate. And we just write a Taylor series expansion of like 1 plus delta to the 4. And you note that, so let's look at these terms. So this term is basically a linear approximation, which is just the gradient term. You have some local curvature, which is defined by the Hessian. And the last term, this defines how the function grows in the long, like far from the original point. And we claim that it's actually these three terms are enough to give a global approximation. And can show that you can actually just lower and upper bound these by the linear term, some factor times the local curvature, and these terms that depict the long range behavior. So it's essentially the gradient, the Hessian, and the p to the p term in the expansion. So this actually captures the long range behavior and the local quadratic, even if you plot it out. Okay. So yeah, this extends to any x and delta, and it also extends to all values of p. So you can basically write this. So you can lower bound and upper bound this by the same terms: the gradient, the Hessian, and these something to the p term. Good. So once we have these, so this gives us good envelopes. So now you can choose to minimize this upper bound to a kappa approximation, and you just do this some log 1 by epsilon times, and you converge to a high accuracy solution. And yeah, we'll see. And this is essentially the same. You can see that this is again like some quadratic plus p term, but it turns out this is easier to work with than just having p objective. Okay. An easy way to think of that is this is somehow more structured, at least around the premise. And the other advantage is we only need to do a very crude approximation to this problem. Okay, so far we have shown that we have this residual problem, and we just need p kappa log 1 by epsilon such problems. Okay. Are there any questions? Okay, so now let's see how we actually solve the residual problem. So yeah, you have a linear quadratic and p term. The first thing we can do is you can do a binary search over the linear term. So we could just convert this to just minimizing under some linear constraints. You have a quadratic and a p to the p term. And we want to use the fact that we know how to solve these problems. So if this is like the LP ball, you want to be able to solve some number of quadratic problems and approximate the solution. So a simple multiplicative weight update solver. So we'll use multiplicative weight update solvers, and the basic multiplicative weight update solver if you would just do the following. You just take some iterations. You look at this quadratic problem, the one that we know how to solve, and you just build the solution. You just update the solution every time based on the solution you get from the quadratic problem. And you update some, these weights that we have. And in the end, you can return the average of this. So this is a standard multiplicative weight update template. If we fit it into our problem, so if we fit this into our problem, you can note that the solution, so if we are solving this problem at every iteration, this solution can actually be off by a factor of m to the 1/2, just because it's almost like you're solving a L2, you're trying to approximate an LP problem with an L2, so this is something like m to the 1, approximately m to the 1/2. So you would need about m to the 1/2 iterations to get to get the solution down to at least a constant value. So this algorithm, if analyzed, this converges in some m to the 1/2 iterations. But if we actually want to do better, we do the small trick, which is also known as width reduction, and it's originally seen in the context of Max Flow about 10 years ago. And the trick is, okay, so if you have if you get a solution that has a large value, so if you have a solution that has a small p-norm, then you build your solution. Otherwise, for every coordinate that is large, you just penalize the weights by a lot. And it turns out that this trick gives you an m to the 1/3 rate of convergence. And it will return a constant approximate solution to your problem. Correct. So what we really did was, you have this problem, we converted to just minimizing the quadratic plus the p term and get rid of the linear term by a binary search. And you can use this fast multiplicative weight update solver to get a constant approximate solution to this problem. Correct. So overall, you can find a constant approximation in some Pm to the 1/3 linear system solves. And this gives us a 1 plus epsilon approximate solution to, in overall, some p squared m to the 1/3. You can use some other tricks to actually reduce this p squared to p, but we can leave that for now. Okay. Right. So you may ask what was really special about LP norms that actually lets us do these two things. And the answer is that you can actually extend these to some structured problems that have the same kind of structure as LP regression. So the main ideas we just used were finding good global envelopes and this fast solver. And the property, so the main bottleneck is maybe this, finding a fast solver that gives, like, which functions are incorporable in these fast solvers. And a sufficient condition is quasi self-concordance, which we also saw on Monday in Ryan's talk, which is some kind of higher order smoothness kind of assumption on the functions. So in simple one-dimensional setting, it just means that the third derivative is bounded by some factor times the second derivative. And this is slightly different from self-concordance. In self-concordance, you have a 3/2 a power on the second derivative. But yeah, for our purposes, you only need to bound the third derivative by the second derivative. And this does capture some important functions that are studied, which is like softmax. It captures logistic regression, and it also captures regularized LP regression. So this is the kind of function we were looking at for our fast solver. So these, so So the key property of why these quasi-self-concordant functions are useful is the fact that it actually implies this property of Hessian stability. So that means that if 2 points are close in space, the Hessians of those points are only like a small multiplicative factors. Okay. And this property actually allows you to say that the function is locally quadratic. So at least in like small L2 balls, or depending on which norm you're working with, in small regions, your function is very well behaved. It's both it has both quadratic upper and lower bounds. Right. And this allows us to give a width reduced algorithm for all quasi self-concordant functions. So let's recap what we saw for LP. You had these few iterations. We were solving this quadratic problem, which was just the Hessian. Essentially, you were solving, this is just the Hessian of the function. And if this was small, the solution had a small norm, you were updating it. And if it was large, then you penalize the weights. So for general functions, you can use the same idea. Now you solve this quadratic problem, but now you have this some regularized Hessian of the function that you're looking at. And you look at the norm of the solution. So if this norm is small, so this is like m to the 1/3, this norm is small, you're building your solution, and you're just updating your weights. But if this is large, so then you look at all coordinates that are large and you penalize the thing you're solving here. And yeah, and in the end, you just return the average of the solution you form. So you can think of this as a primal step and this as a so-called dual step in terms of optimization. And we can prove that these basically give you a rate of convergence of some m to the 1/3 and some constant. So you can find a constant approximation in some m to the 1/3 iterations. So these kind of algorithms have actually been seen in many contexts. So we have seen it in the sense of, so we have seen it for max flow. You've also seen, so these have also been seen for some matrix scaling applications and some, matrix scaling, operator scaling kind of problems. And but they all have these very different specific potentials that they use. So what we actually show is that you can give a unified potential analysis and so you can do a unified potential analysis and that captures all quasi self-concordant functions and it gives us these rates for, so for infinity regression, you can do m to the 1/3 by epsilon to the 5/3. For LP regression, we recover the rate we know. And for logistic regression, again, you can do the m to the 1/3 linear system also. Okay, so the key ideas are, again, we extend these multiplicative weight update algorithms, and you need a new potential, a unified potential analysis that can handle all of these. And there's also since these multiplicative weight update schemes only give you like constant approximations, you also need a way to boost these to through high accuracy solutions. And you can give a new version of iterative refinement. But the difference now is you can't get these global upper and lower bounds, so you have to work with local bounds. And with these local bounds, which can be termed as some box constraints, you can boost these to high accuracy solutions. Okay, so now I'm going to talk a little more about what else can we get from iterative refinement. It's not just the high accuracy solutions, but it has some more interesting consequences. So usually, okay, so far we were just solving these LP regression problems using linear regression, like just solving L2 problems. And that, since the gap between these norms is something like m to the 1/2, you're able to speed it up to m to the 1/3. But suppose you could use some higher part. Suppose you want to solve the L10 norm using some L4 norm or something. So the gap between these norms is already low, but classically, if you just have these LP problems, You cannot directly solve these. These give you a factor of some m to the p by q. And this is actually large. So if you think of p as 4 and q as log n, oh, sorry. Oh, I think the other way around. I want p to be log n and q to be 4. Then this factor is basically quite large. But you can, the thing you can show is that you can solve with an extra factor of m to the 1 by p minus 1 by q. And this is small. And if you use problems of this form, so instead of just directly solving the p and q, if you use a regularized version, you can solve these. So you can directly solve this problem using something that's minimize x square plus x to the q for any p and q. You can do that with only an overhead of 1 by p minus 1 by q. And this is good in the sense that if we go back to our iterative refinement framework, we created these residual problems. Now, if p is very large, you can just reduce it to solving for the log n norm problem, and you can solve that. So this basically lets us get rid of one p factor in the overall algorithm as well. So yeah, you can solve the q residual problem. That directly gives you this approximation. And this allows us, this gives some relation for different problems for different p values. And for large p, we just solve the log n. This is it. Okay, so yeah, this allows us to, give this linear in p m to the 1/3 linear system solve. Okay, so one more advantage of using these multiplicative weight kind of frameworks where you're solving linear systems is you can use like these routines or these data inverse maintenance data structures that kind of that allow you to speed up algorithms by not solving the quadratic problem at every iteration. So the current time we have that solves this is something like m to the 1/3 plus omega, where omega is the matrix multiplication time. And we can design data structures by using some inverse maintenance that solves this in some polylog m times m to the omega time. And all of this is possible because we only need to solve the residual problem to a constant approximation or a log m approximation. And this allows us to find high accuracy LP regression in some m to the 2.33 plus m to the omega. And this for the current matrix multiplication is just m to the omega time. Okay, so on graph problems, which are like nicer instances, we can do a lot better. So let's look at these problems where you again want to send one unit of flow from some S to T, but now instead of minimizing a quadratic energy, you're minimizing the LP energy of these. And in this case, if you directly apply our algorithm, you get some m to the, you can solve linear systems. The linear system you need to solve here is a Laplacian linear system, which we know how to solve in near linear time. So you get something that's m to the 4/3 total runtime. And you can also show that you can improve this by using sparsifiers for graphs. So you can put this back in the framework, you put it back in the iterative refinement framework, you get the residual problem. We can use some tools from this paper that appeared in stock, and that gives us sparsifiers for the residual problem. And once you have the sparsifier, you can just solve that. So it reduces to some m plus n to the 4/3 time algorithm for these weighted LP norm flow problems. So further work on this, these were for graphs. So if we ask about sparsification, there has been some further work last year by Arun Yang and Aaron, where they're able to reduce the iteration complexity from m to the 1/3 to n to the 1/3, even though we're still using the same linear system. And they're basically basing this on, so they have a new interpretation of Lewis weights. So you can work in the smaller space instead of the larger space in terms of iterations. So you can change all these potential analysis to be working in the smaller space by just initializing the weights to the lowest weights instead of, let's say, whatever we were using, 1 or 1 by n. And once you initialize them to the lowest weights, the weights are already in the smaller space, and they also require some new energy, some new tools in terms of the width reduction. So the weights increase fast enough in the smaller space. Right now, the weights increase in terms of the m space. So with these, they're able to get this up to m to the omega into the 1/3 total time for all p greater than 2. And so yeah, this is so far the thing we know about these sparse problems. And yeah, so now if we move on to more algorithms in practice, so from this framework we can actually get some fast algorithms in practice. And so we look at these bunch of algorithms, which are these iteratively reweighted least squares algorithms. So these basically look at weighted linear systems, and they solve a different weighted linear system in every iteration. So it's kind of like what we're doing, we're handling some weights, solve a linear system, and move to the new iteration. But the standard algorithm just looks at this problem and thinks of this as a fixed point iterate. So instead of minimizing this, it thinks of this as a fixed point iterate. But since we don't know this value, it inspires this iterative algorithm. So you're looking for something. So if this is the plane, you want to find something that touches this plane. So right, so this, since we don't know the optimizer, this inspires this fixed point iterate. So you start from some x, you solve this problem, you get a new solution, and you move to that solution. And you can continue this process. So this is classically known as the iteratively reweighted least squares algorithm. And it has been studied for over 60 years, I guess, 50 years. And this algorithm, it's known to actually, for small values of p, so for p between 1 and 3, we know that this converges in the limit, but we don't really know the rate of convergence. But in practice, it has been seen to converge quickly. But for large value, not even large, something really small like 3.5, you can find very easy random instances for which this diverges within 10 iterations and it does not converge. So there's basically, it for a long time, we didn't really know how to find such a weighted least squares algorithm that converges reliably and to any solution. So we can show that we can actually, using this iterative refinement framework, we can find an IRLS method that provably converges in very few iterations. It certainly works well in practice because we know how to, over time, we know how to solve these linear systems really fast. And the rate of convergence is not this m to the 1/3, but you can show it converges in m to the 1/2 iteration. And in practice, you can see that it's much faster than the theoretical bounds. And the algorithm we use is actually not very different from the original algorithm. So instead of solving, so you solve the weighted linear system. Instead of just using the weights they use, we add a small systematic value. So this S we control based on how much progress you're making to the solution. And you use the original weights. And you just solve this. And once you get a solution, instead of directly updating to the solution, you look at this direction and you do a line search along this direction and you find the point which has the minimum objective value along this direction. And these two tricks have actually been used in some applications, like this line search trick is used usually in practice. Here they sometimes add some Gaussian noise, but it's still not guaranteed to converge. So in this, you just do this, you find a weighted linear system, small constants, and if there's some insufficient progress, you control this constant. And in practice, this has proved to be pretty good. So we look at two kinds of instances, and for some graph instances and some random matrices. So some random graphs in high dimensions, some matrices. And for even large values of P, you can see that it actually converges. The error converges quite quickly. You can even get down to 10 to the minus 12. Actually, you can get down to more. And in practice, we also see that the running time scales linearly with P, even though our bounds show that it's something like P to the P cubed or something. And with the dimension, it looks like it's almost increasing like a constant. It's not increasing too fast. So in practice, it seems much faster than what we find. And compared to whatever algorithms we have for these problems, this was 10 to 50 times faster, even on simple computers. So yeah, so you can see that for P equals 50 and some size 2500, can show that it converges to some accuracy of 10 to the minus 30 in some very few iterations. Okay, so I'm now going to look at some other approaches on obtaining these m to the 1/3 iterations, some follow-up works on these. And so most of optimization is, people usually study these in the context of these gradient descent or these, not exactly gradient descent, but these acceleration kind of algorithms. And in 2020, there was a work that uses this ball oracle approach that gives these m to the 1/3 kind of rates for all these quasi self-concordant functions, including LP regression. So this oracle is slightly different. So in our case, we're solving these linear systems. Now they're looking at this oracle where, okay, suppose you're given the minimizer of a function in this small, in a ball of radius r, then how do you optimize these functions? And a simple algorithm would just be, okay, you take a point, find this minimizer and move to the new point. And this can be shown to converge in something that's, yeah?
What's the norm?
Oh, here I think at the original work uses Euclidean norm, but I think they can do it with any norms at this point. So yeah, this one basically converges in, so the initial distance to the optimizer versus the ball you're looking at, and you can go at a log 1 by epsilon rate. And if you can use some Montero-Schweiter kind of acceleration techniques and accelerate this to some this value times 2/3 to the power 2 by 3. And you can think of this term as something like m to the 1/2. Yep.
Oh, just this one depends on the norm. The first bound does not, the second one does.
Okay,
Oh, yeah. The first.
so you can do acceleration in a two norm,
Correct.
but it's not clear in other norms.
Correct.
Is there, you think it's impossible? Or?
Happy to discuss after. I guess you could ask about acceleration of L infinity gradient descent without, when you only have a gradient oracle. It's maybe a reason, but that's not a proof, and I don't think it's known.
Yeah.
What do you assume for F here?
Assume for? F here. So, I mean, I think you could do it for both things, but if you want to be able to implement this ball oracle, it should, one way to implement this ball oracle is if F is quasi self-concordant. So as quasi self-concordance kind of implies this local quadratic structure, right? So you could just think of it as, okay, in this ball, if it has a local quadratic structure, you can use anything like accelerated Newtons or any method to find even very high accuracy solutions. Okay, so yeah, so using some sort of Montero-Schweiter acceleration, you can get this down, and this can be thought of as, this term can be thought of as m to the 1/2, and then power 2 by 3 gives you the m to the 1/3 rates. And in this model, there are actually no lower bounds that these kind of rates are optimum. There are lower bounds that are proven, which is why, and since for QSC functions, this is kind of like solving a bunch of quadratic problems, we believe the rates are optimum, even in the multiplicative weight framework. Okay, good. So yeah, some natural open problems. So it's always open to figure out whether for P1 and infinity, if you can do high accuracy with m to the 1/3, and or like show that it doesn't exist. And this would directly imply faster linear programming. But yeah, or even actually not just P1 and infinity, it's even open to directly give m to the 1/3 kind of rates for P less than 2. So you can make the iterative refinement work even for P less than 2, but we don't know how to make this multiplicative weight update method or any other low accuracy solver to work, or even the other algorithms that are based on mirror procs. They also work for P greater than 2, and using a dual, you can do P less than 2, but there's no direct method known. And so yeah, maybe one way to think of finding faster IPMs is if you could actually write these algorithms as an IPM. Because we know there exists m to the 1/3 higher accuracy, could ask that if you could write this as an IPM or something. And the other question is, okay, so instead of solving linear systems, can you solve some other, use some other oracle, like maybe like solving a 10 norm or something, and can you achieve accelerated rates by that? So far, we only know how to achieve this non-accelerated m to the 1 by p minus 1 by q, and you may ask, can you accelerate that? And yeah, and the next talk, which is going to be about dynamic least squares. So we know how to do some things for dynamic least squares regression. So in terms of changing inputs, we don't know much about any other regression problems so far. So it still remains open. So yeah, to summarize, we saw these good envelopes for LP regression, found a fast high accuracy algorithm, and we can extend these to quasi self-concordant functions and use inverse maintenance to get faster solve LP regression almost as fast as linear regression. And we also have a fast algorithm in practice. And yeah, that's it.
Questions now from the audience? Additional questions?
I think this is a really naive question, but I lost where for like P being infinity, why don't you get a high accuracy algorithm by just like setting P to be some log n over epsilon or something? Or-
Good. So you have a linear dependence on P in the algorithm.
Yeah, right.
So if you set P to be log n by epsilon, that already gives you a 1 by epsilon.
Oh, this is like, oh, okay. I got it. Okay, so
Yeah.
it's like poly 1 over epsilon or something.
Yeah, it's still
okay.
poly 1 by epsilon.
Thanks.
So maybe just a comment there. Yeah.
There are some settings where that is indeed like one way to obtain an optimal or like the best known algorithm. Like this is state of the art for, or was at some point state of the art for undirected max flow.
Yeah.
Anybody else? Well, if not, then we thank the speaker again. Is this a short break?